In this lesson, we're going to extend our cost and revenue discussion to talk about marginal cost and marginal revenue. First off, a cost function is generally not a linear function. Usually, as you produce enough quantities of a good, it becomes more efficient than producing smaller quantities. You may also have an extremely high production levels. There might be a scarcity of resources, or something that makes it so that it gets more expensive once you have extremely high. So with that said, it's not unusual to see a cost function that might look like this. It's concave down and then concave up. You might also have a revenue function that's nonlinear. Remember that if revenue is based on demand, we got some sort of parabola. But even if you have a fixed price, sometimes you can have a market that gets so flooded that the price has to be decreased in order to keep selling. A lot of things that get sold enough will eventually have a price drop. Video game consoles are my favorite example. Here's a simple example of the cost and revenue functions for a particular company shown in this graph below. We want to know where is the company making a profit. Remember that profit is revenue minus cost. So anytime your revenue function is higher than your cost function, then you're making a positive profit. Where on this graph is revenue higher? Right here in this range, between the 130 and the 215. A profit is made when 130 to 215 units are produced. So the question that we want to figure out is not so much how do I make a profit, but how do I make greater profits? How do I increase my profits? We often call this marginal analysis. So let's suppose in this example we have an airline company deciding, do we want to add another flight in a given day? We figure out how much will it cost us to get that additional flight, and how much revenue would they get for creating that additional flight. And the idea of additional is the idea of marginal. Remember in our original marginal cost definition, we said it was the cost associated with making the next item. Now our official definition will be the marginal cost is actually defined to be the derivative of the cost function, C prime of Q. And the way that we interpret it is how we were interpreting derivatives previously. It's the cost to produce the next item. So the marginal cost is the derivative. With that said, we now have four things that all mean the same thing: derivative, instantaneous rate of change, slope, and marginal. All four mean the same thing. And just to point out that these are fairly similar, if we were to consider the tangent line right here, the tangent line and the actual cost between 100 and 101 have a very small gap between them. That small gap is enough that we can use the derivative to help us make our estimations. Similarly, we will define the marginal revenue to be the derivative of the revenue function. Same thing as last time, it is generally looked at as the revenue when producing the next item. So now let's go a little bit further on that airline. The airline is trying to decide if they should add a 101st flight. And they looked at their cost and revenue graphs, and they got a picture that looks like this. The revenue function has this slope right here that is very important. Remember, slope means derivative, and marginal means derivative. So the slope of this little tangent line is the marginal revenue. Similarly, the slope of this little line represents the marginal cost. Whichever one has the higher slope is the one that represents the bigger quantity. Notice that the slope representing the marginal revenue, or the slope of the revenue function in general, is the higher one in this case. Since the revenue has higher slope, this means marginal revenue is greater than marginal cost. So now let's interpret that. The marginal revenue is the revenue from the next item. The marginal cost is the cost associated with the next item. So in this context, that next flight, or the 101st flight, if you will bring more revenue than cost. They should make it. So there we have it. Make the 101st flight. That will actually be beneficial because we'll have more revenue than the cost. But I do want to point something out. Even if the costs were higher for that 100th flight, even if the costs were higher, if the revenue of the 101st flight is better than the cost of the 101st flight, they should still make that 101st flight because they will make more money on that flight than it cost them. Even if the overall picture says that the cost is higher, it's making the loss less. So it's better to move forward if the marginal revenue is higher, no matter what is going on in the overall revenue and cost functions. For the next example, let's look just at a cost function. Does it cost more to produce the 500th item or the 2000th item? That's a marginal cost that we're talking about, and technically it would be the marginal cost at $4.99 and $19.99. I'm not worried about that technical thing because look at the scale of the graph. But if we want to know the marginal cost, that means we need to be thinking about a derivative, and because we're thinking about a derivative, we should be thinking about slope. So let's look at the slope at 500 and at 2000. I've drawn some small segments to represent that slope. Notice that the slope at 500 is definitely higher, so the question of which one costs more, it's the 500th item. Since the marginal cost, which we found by looking at slope, is higher at 500, technically $4.99. Like I said, think about the next. Regardless, the 500th item is definitely more expensive by considering those slopes. Let's do the same thing with 3,000 and 4,000. I've drawn in a couple more segments in green to represent these. Now if you notice, the 4,000 has a higher slope than 3,000. So for the same reason, the 4,000th item is more expensive. Now the last question, at approximately what production level is the marginal cost the smallest? And what is the total cost at this production level? Just looking at the graph, this is actually whenever the concavity changes, if you're trying to be really specific. But I would say the place where the slope is smallest is right about 2,000. So where that slope is smallest, the marginal cost is smallest. The cost per item is smallest. The slope seems smallest at 2,000, so this is the quantity with the lowest marginal cost. The question also asks, what is the total cost at this production level? The chart is actually telling us the total cost, so if we just come right over here, we see that that would be $10,000. To finish off this lesson, let's consider the cost and revenue functions as a graph and consider what the marginal cost and marginal revenue functions would look like. Remember, marginal is just a derivative, so all I'm really looking at is finding a derivative. This first function appears to be a cost function, and the second one appears to be a revenue function, so we'll use that. To make the cost function, for this example, I'm actually going to try to estimate the slopes. Again, this is not something I'm asking you guys to do on a regular basis, but I'll just try to estimate it. I've drawn in a few representative lines that I think represents the slope decently well. And then I'm going to draw some points that are going to represent those slopes on the derivative graph below. These points represent the slopes at decent ability. And then if I draw the curve that passes through these things, that is what I would call the marginal cost function. Now the revenue is going to have an easy derivative. Notice that this thing is a straight line. And straight lines have slopes. In this case, the slope, you could say, rise over run is 5 over 3, and there's a nice clean point. That would say that the slope is 5/3. So the function is going to be a straight line through 5/3. There is your marginal revenue function. Because it has a constant price, it has a constant marginal revenue.